Good morning. Today we would like to talk about the GPU-based large-scale similarity search. Currently, there are billions of photos and images are popularized on the internet with different features and names. The duplicate photos and images are waste storage space. Therefore, deep learning is applied to recognize the pattern by using huge number of data to making recognition and classification possible. Also, to reduce some storage resources. And in this semester, compared to the last semester, we have mainly focused more on about the configuration of ImageNet dataset and the baseline of HDCNN model. There are two main objectives. First is to know the whole learning baseline of the hierarchical deep convolutional neural network, which is HDCNN model. And the second, to get some sample results on some network structure based on two datasets. One is CFA100 dataset, which consists around 60k image, and the other one is the ImageNet dataset, which consists on about 150k image. We are use a several method. First is the cafe because last semester we have already using the cafe model to construct our model and the network. So we continue using cafe to coherence the result compared to the last semester. And the second one is the graphic processing unit, because our project is mainly using GPU based. So we continue using the GPU to do the image recognition and classification. And the third one is to prepare the some CFA100 dataset, the ImageNet dataset, because using these two datasets to fit in the network structure is really important. So we need to prepare some data preparation, processing, augmentation, etc. My groupmate will to present later on, and so as to let the model can construct successfully. And the fourth one, we need to compare the model of CNN and HDCNN. Before that, let me introduce about the HDCNN architecture. HDCNN architecture is designed to the minimal of the structure of category hierarchy, where fine categories are defined into the cost category, perform end-to-end classification, and it mainly comprised into four parts. First is the shared layer. They used to receive raw image pixel as input to extract low-level features. Basically, it is the same as the preceding layers in the building block net. And the second one is the cost category independent layer. It is the same as the raw layer in the building block CNN to produce a fine prediction, which means they can produce their own prediction that the corresponding image should belong to the which category, so that there is a cost category probability. It is used for combining the prediction made by the fine category components. Moreover, it can enable the conditional execution of fine category components whenever they hold, while the probability is really large. Thirdly, are the set of the fine category classifier, the independent layers to make their own fine category prediction. Except in the final classification layer, numbers of filters are set into the partial set. The configuration of the layer are mostly same as the building block CNN. The reason behind why both coarse category component and fine category components are shared common layer, since when extracting low-level features are useful for the both coarse and fine classification. In the training part, we also need to do the extra step to extract the features to increase some accuracy while doing the testing of the model. Moreover, sharing the common layers can reduce floating point operations, the memory footprint of the network execution, and the number of HDCNN parameters to increase the efficiency and the accuracy of the HDCNN training. So as you can see, there are some similarity and some difference between CNN HDCNN network, but HDCNN model. But the HDCNN model are defined into more parts that can increase the accuracy to let the final prediction can be more successful and accurate.
Okay, I will now talk about the experiment and the results. To start with, we will have to do the data preparation by converting the data set into the LMDB or the level DB. And in the Cipher 100, we have converted the data set into 148 level DBs after the ZCA whitening and global contrast normalization. The ZCA whitening can reduce the dimension of the image for easier identification. The global contrast normalization can normalize the image to eliminate redundant data and make the dataset more consistent. And for the ImageNet, we split the ImageNet into the training set and the validation set before converting them into the LMDB. We also train the data by separating the classes using course category classifier and distinguishing the difficult class with using the fine category classifier. To increase the sample size, we will do the random crop and the flip horizontally, which can further increase the sample size. And we also use the conditional executions in the HDCNN model. This conditional execution will add some drop layers between the convolutional layer. So if the data set or the layer that features is not very relating to the image, then the layer will be dropped. So this can fasten the computation time. Also, we also use the parameter compression to reduce the parameter in the model, so we don't have to store too much data inside the model. And finally, we have the accuracy comparison table. After these 2 semesters, we found that data with the CNN model with data augmentation is more accurate than the one without the data augmentation. Besides, with using the same NIN network, we found that the ImageNet data has a higher accuracy. And also, when comparing the HDCNN using NIN blocks and the normal NIN model with the Cipher 100 dataset, we found that it has about a 4.4% accuracy increase, which is very significant. We take this result because we think this is because of the data pre-processing before we putting the dataset into the CNN model. And to conclude our research, we found that using different network structure with minor changes will affect the outcome performance and the training duration. And also, by using the data pre-training, we will have a more accurate result because we can separate the image into a coarse category and fine categories, and then after that we compute the average result. And also, the techniques we used in this model is very essential for the future usage. And for the future directions, We may also try the BCNN model and also construct our own model to improve the large-scale performance by pre-training the dataset label, fine-tuning with the snapshot of training, because this after training the model first, then we can get the snapshot, and then we input the snapshot to another model. This will further increase the accuracy, we think. And also, we will extract the features or do more comparison on the data augmentation. In the end, we would like to express our deepest appreciation to our supervisor, Professor Lin, for his general advice. Thank you.